So now we're going to talk about the intermediate value theorem. So suppose that f is continuous on the closed interval a to b, and let n be any number between f of a and f of b, where f of a is not equal to f of b. Then there exists a number c in the interval from a to b, such that f of c is equal to n. Okay, so if we look at the two graphs we have here, the difference between a and b, same idea. Okay, so we have f of a, we have f of b, and then at some point there's an f of c that's equal to n, and n is between f of a and f of b. In graph A, we can see that the f of c is equal to n once, and that happens right, if I could click in on it, here we go, it happens here. But in graph B, we can see that there are multiple c values that have the same n. So here and here and here. So it has to at least once be f of c is equal to n, but there can be multiple c's that have the same n value. So let's look at another definition of it. So if a function is continuous between a and b, then it takes on every value between f of a and f of b. So because the function is continuous, like the graph shown here, it takes on every y value between f of a and f of b. So the idea here is that it must be continuous. You must have a continuous function. If it's not continuous, you can't use the intermediate value theorem. So thinking about the weather, let's say, right? So if I wake up in the morning and it's 60 degrees, and then at noon it's 80 degrees, is there some time between when I woke up and noon where the temperature is 70 degrees? Well, yes, because temperature is continuous, right? You can't jump temperatures. It might go really fast through the temperatures, but it's not going to skip a temperature. All the temperatures will be gone through in order. So if I wake up in at 60 and then later on in the day is 80, it must go through 70 in order to get to 80. So that's an example of the intermediate value theorem. So let's look at another example. If I was 20 inches tall when I was born and am 5'8" now, was I ever 4 feet tall? So first thing we want to ask ourselves is this a continuous function? So as time goes on, does your height increase continuously? Or do you skip any heights? Well, you're not going to skip any inches, even though you might be a certain inch for 2 seconds if you're having a growth spurt. You're going to go through every inch. So yes, there is a point where you'll be 4 feet tall, and so I'll write this out, but we can also talk about it. So yes, and we want to make sure that we're explaining why. So I'm going to say because height versus time, which is what this graph would be if we were graphing it, height versus time is continuous. And then we can just say that it's continuous, that I was 20 inches and am now 6'8". At some point between birth and now, I was 48 inches tall. Okay, so just for, I'm not going to really write everything out, but you guys can. But the main idea here is you want to say yes, and you want to back it up based off of if it's a continuous function or not. So since it's a continuous function, yes, at some point you were exactly 4 feet tall because you went from 20 inches to 5'8". Okay, let's look at another example. If I have a bank account that started with $55, but today has $1,000, am I guaranteed that there was a time when there was exactly $500 in the account? Now this one, if you think about it, is not continuous. You're not continuously putting in $1 every day. So sometimes you might deposit $100. Sometimes you might deposit $5. It really depends on the day. So are you guaranteed to have exactly 500? No, because it's not continuous. So if this was continuous, 500 would be between 55 and 1,000. However, we're going to say not necessarily. Could you have $500? Sure. Are you guaranteed? No. So not necessarily, and I'm going to just say that deposits are not continuous. Okay. It could be continuous, like I said. You could be depositing $1 every day, and then yes, you'll have exactly $500. However, most likely that's not going to be true. Okay, so what will we mainly use this theorem for? So it's all well and good that we know that heights are going to be continuous and the temperature is going to be continuous. But really in calculus, we care about the intermediate value theorem to explain the existence of zeros and whether zeros exist or not. So if f of x is continuous on a to b, and if f of a and f of b are non-zero and have opposite signs, then f of x has a zero in a to b. So basically what this means is you have a zero if you check two numbers, a and b, within your function, and one of them is less than zero and one of them is greater than zero. If the signs are opposites, that means that at some point your graph has to cross through zero in order to change signs. So let's look at this example here. First off, we have to always check to see if it's continuous, because if it's not continuous, you can't use the intermediate value theorem. So here we have a polynomial function, right? It's a cubic. So you should know, hopefully, from Algebra 2 or pre-calculus that polynomials are always continuous. So I'm just going to write that over here. It's continuous because it's a polynomial. Okay, so we want to find the root. So show that there's a root of this equation between 1 and 2. So 1 and 2 are our endpoints. That's the a and the b. So what I'm going to do is I'm going to find f at a. So I'm going to do f at 1. So all I'm going to do is plug in 1 for all the x's. So I have 4 minus 6 plus 3 minus 2, and that's going to equal negative 1. And that's a negative value. That's less than 0. I'm going to do the same thing for f of 2. So I'm going to plug in 2 for everything. So I'm just going to get 32 minus 24 plus 6 minus 2. And that's going to equal 12. And that value is greater than 0. Okay, so we found that f of 1 is less than 0. And that f of 2 is greater than 0. So this is proving that there exists some 0, or there's a root to the equation between 1 and 2. So at 1, it was less than 0. At 2, it was greater than 0. At some point, our graph must cross exactly 0 to go from negative to positive. So this, using the intermediate value theorem, proves that. So now we're going to look at an actual AP question that involves knowledge of the intermediate value theorem. And don't panic. I know this might be one of the first AP questions you're seeing. Okay, so let's just read it first. So we have that water is being pumped into a tank at a rate modeled by W of t equals 2,000 e to the negative t squared over 20 liters per hour between 0 and 8 inclusive, where t is measured in hours. Water is removed from the tank at a rate modeled by R of t liters per hour, where R is differentiable and decreasing on 0 to 8 inclusive. Selected values of R of t are shown in the table above. At time t equals 0, there are 50,000 liters of water in the tank. Okay, so right now it's a lot of information. Basically what's going on here is that water is getting pumped into the tank. Also, water is being removed from the tank. So the amount of water in the tank is dependent on the water going in and the water going out. Okay, W of t is the water going in. They gave us a function for that. R of t is the water going out. They did not give us a function. However, they gave us this table with some values. So the question that we're asked here is, between 0 and 8 inclusive, is there a time t when the rate at which water is pumped into the tank is the same as the rate at which water is removed from the tank? Explain why or why not. So this might seem tricky. It might be confusing what we need to do, right? It doesn't ask us to use the intermediate value theorem. But typically when they're asking you a yes or no question, like is there a certain time between an interval, we're going to be using the intermediate value theorem. So the first thing we have to do is make sure we know that this is continuous, because if it's not continuous, then we can't use the intermediate value theorem. So we're going to look at W of t. Okay, so here we have this function, and it's between 0 and 8. So on the interval from 0 to 8, this is continuous. Okay, and R of t, it tells us it's differentiable and decreasing. So this differentiable, we're going to talk about that more later. Basically, if it's differentiable, it's continuous. So it's telling us that everything is continuous. So since it's continuous, we can continue. So we need to figure out how much water is actually in the tank, right? So if water is being pumped in and water is being pumped out, we can say that the amount of water at any given time in the tank is going to be W of T minus R of T. So the rate of the water being pumped in minus the rate of the water being pumped out, that's going to be the amount of water that we have in the tank. So because we have this interval from 0 to 8, what we're going to do is we're going to use the intermediate value theorem and use 0 as our A value and 8 as our B value. So first thing we're going to do is evaluate this at 0. So we're going to do W of 0 minus R of 0. So W of 0, all I'm going to do is plug in 0 into my W function for T, and I'm going to solve it, and that's going to give me 2,000. And then I'm going to, for the R function, R of 0, I'm going to use the table. So at 0, my R is going to be 1340. So when I subtract this, I don't really care about what the value is. I just care about the sign. So I know that when I subtract this, I'm going to get a positive number, and it's some number greater than 0. I'm going to check it at the other endpoint now. So I'm going to do W of 8 minus R of 8. So W of 8, again, use your W function here, plug in 8. So that's going to give us 81.52. I'm going to subtract R of 8. So again, I'm going to use my table. So minus 700. And then once again, I don't care about the actual value, but I know that when I subtract these, I'm going to get a negative value, which is less than 0. So since I've checked both endpoints, the 0 and the 8, and I see that the sign does change, it goes from positive to negative, at some point between 0 and 8, some t value, my W of t minus R of t is going to be exactly equal to 0. Okay, so the amount that's the rate at which the water is being pumped in and the rate that the water is being pumped out at some point will be equal. Okay, so as far as the scoring guidelines, let's look at this actually for the scoring guidelines. Okay, you get a point if you consider W of t minus R of t. So if you understand the idea that the water in minus the water out is something that we need to use, and then one answer with explanation. Okay, so there's different ways you can explain it, but you want to make sure you test the endpoints, right? That's what they did here. They got that tested at 0 is greater than 0, tested at 8 is less than 0, and we know it's continuous. So since it changes signs, the intermediate value theorem guarantees at least one time for which W of t minus R of t is equal to 0.